Alrighty, we are on chapter 14, which is the start of the best part of all of physical science, because this is about, we're going to go into our chemistry section, which is my favorite because I studied chemistry in college, biochemistry. So, this is my favorite stuff, and I know a lot about it, more so than I do all the other stuff we've talked about so far. So this is the jam, guys. So we're going to start with learning about solids, liquids, and gases, and then we're going to move on to the more actual chemistry kind of stuff. Just an introduction. This isn't a chemistry class, but it will be an introduction to chemistry so that when you get to chemistry, maybe it will be a little bit easier. So first we're going to start with kinetic theory. So kinetic theory is an explanation of how particles behave. And we're going to learn that these particles, this word particles, these can be all sorts of different things. They can be, we're going to call them atoms. And atoms make up what is called matter. So you do already know the definition of matter. It's anything that has mass and takes up space. That should be a refresher for you. I don't think that's new information. Hopefully not. If it is, then you should take a note of that. Okay, so there are four facets or parts to the kinetic theory. And the first one says that all matter is composed of tiny particles called atoms. All matter is composed of tiny particles called atoms. Okay, so atoms make up matter. Atoms are not the smallest component of matter, because we're going to see we have these things called subatomic particles like electrons, neutrons, and protons. And then we have things like quarks and leptons, which make up protons and neutrons. So we're going to see that they're not the smallest building block of matter, but they are the one we refer to quite often, atoms. So that's the first one. The second one is that all atoms have energy. So all of the atoms that make up everything, even, anything you can think of, every single atom has energy. So atoms make up things like our bodies, right? So every single atom, not cell, atom in our body contains energy. Every single piece of fruit, every single animal, every single wall in the school, every single piece of sand out in the desert are all composed of atoms. And every single one of those atoms has energy associated with them. Even the ones, the atoms that make up solids, like pieces of sand, or like ice cubes, or like the walls of the school, they all have energy associated with them. And something you probably wouldn't think of, or haven't thought of, is that the air that you're breathing, that is all atoms. Those are all atoms that are making up the air that you're breathing. And all of those atoms are also have energy associated with them. The atoms, the water in your water bottle is all made of atoms. Every atom has energy. I think you get the point. So that's the second facet of the kinetic theory. The third one is that this energy causes atoms to be in constant random motion. Okay. Also, my husband is listening to me record this lecture, and he just said, "Taylor, you just said water in their water bottles, but it's Ramadan." So, my bad, sorry. Water in anything containing water, just a random water bottle. Anyway. So, that's the third facet, that this energy causes atoms to be in constant random motion. So, even the atoms that make up ice cubes are in constant random motion. Even the atoms that make up the walls of the school, the big rocks that you see, they're all in constant and random motion. They're vibrating. They're not moving as much as other particles like liquid particles or gas particles, which we're going to learn about here in a little bit. But the solid particles are even moving. So that can be a tricky one for some people. The fourth facet is that the more energy that is in these particles, the faster the particles move. So this makes sense with if you think about it, because so for example, right after or in the middle of a soccer game, you have a lot of energy. You're moving really fast. You're running, right? You have a lot of energy in your muscles, and your lungs are pushing air out. There's a lot going on in your body, right? You move really super fast. But think about how your body moves on a really cold morning, right when you wake up and you're slowly getting out of bed and you're like barely moving, right? Well, you don't have you've been laying down. You've been not moving at all, right? So there's not a lot of energy associated with your body at that time, right? So you're moving slower because you have less energy, right? First thing in the morning, as opposed to when you're running down the pitch in a game. So that's just one way of remembering that rule and kind of understanding it a little better, or that part of the theory. So remember, I just want to say something really quick, that the word theory does not mean guess. Don't forget that. So this is called kinetic theory, but it's not, this is how atoms behave. These are all true things that can be seen and have been seen over and over and over again. So don't get confused or bogged down by that word theory, because remember, we learned this at the very beginning. There's a scientific theory does not mean that it's a guess, okay? All right, so just wanted to point that out. Okay, so we need to understand these four things. What does this have to do with matter or thermal energy? Well, we have to understand these four things in order to really be able to talk about and understand the properties of solids, liquids, and gases. So that's why we are starting with this, and now we're going to do a little bit of vocabulary that we're going to need to know also in order to discuss the different states of matter, the solids, liquids, and gases. So I think most of these will be a refresher for you, and there's going to be some problems on your homework, so hopefully that involve these words and applying them, not just knowing the definitions. So first we need to know what volume is and what it's measured with. So volume is the measure of the amount of space a substance takes up. Sometimes you might hear this volume as the measure of the amount of space that a substance occupies or a substance takes up. Those are synonyms, or in this case they are. So that's what volume is. Volume is how we're going to measure liquids. So when we're talking about the amount of a liquid, we talk about the liquid's volume. And the units that we talk about liquids with are, most common would be milliliter and liter. But we also have this weird one, centimeter cubed. That's a very common one also that we see in chemistry a lot. So those are the three main units of liquids. Remember that you should remember there's 1,000 milliliters in 1 liter, and there's 1 milliliter in 1 centimeter cubed. So those are the conversions that you're going to need to know and remember. Okay, so volume is pretty simple. Let's look at, I'll give you a couple examples. We can have 10 milliliters of water, for example. Sorry, I forgot. This is the measure of liquid and gas. I don't know why I didn't write that. This is the measure of liquid and gas. So we can have 10 milliliters of water. We can have, let's say, in a balloon, we can have 1 liter of air, which is a gas, right? So we talk about gases and liquids. Sorry for forgetting that. That's very important. We talk about liquids and gases in volume. Okay? So we're going to see more of that when we actually talk about liquids and gases, but for now, this is this is good for now. Okay, the next one we need to talk about is mass. All right, so mass is the amount of matter in an object, or we'll say in a substance because it's not necessarily in an object. So we can measure solids, liquids, and gases by their mass, but most commonly we're going to just talk about solids when we're talking about mass. And the units that we're going to see often when we're talking about mass are grams. That's usually what we're going to see in chemistry. We could see milligrams or micrograms even when we're talking about really tiny amounts. Okay, as some examples would be like a piece of iron is 100 grams. 100 grams of iron. Or a coin is made out of 280 grams, or we'll say milligrams, of copper. So there's lots of different ways we're going to see mass used. Okay, then we have density. Density is the mass per amount of volume of a substance. So this, we can measure all solid, liquid, and gas. Or we'll say solid, liquids, and gases all have density. And there's an equation actually for density. Whoops. And it's literally just density equals mass divided by volume. So the density of of 10 milliliters of gas that contains 2 grams of oxygen. I said that solids are usually measured in grams, but we also are going to see liquids and gases measured with grams as well. So 10 milliliters of a gas containing 2 grams of oxygen. In order to find the density of that, what's the density of this oxygen in this gas? The density would be the mass of the oxygen, which is 2 grams, divided by the volume of the oxygen, which is 10 milliliters, which would give us a density of 0.2 grams per milliliter of oxygen. All right. So I think you understand what things that are more dense than other things. For example, obviously solids are more dense than gases, right? Because gases, their particles are very far apart and they take up a big volume. They have a small mass, but they take up a huge volume, whereas solids have a really big mass and a very small volume. They occupy a very small amount of space. So we're going to make an amendment here, and we're going to say liquids and gases, because we can talk about all of these in terms of mass, and we're going to go back to our volume, and we're actually going to say and solids here, but it's just not as common. But solids do take up an amount of space, but usually when we're talking about solids, I wouldn't say, oh look, there's a a liter of rock right there, right? I would say that's a 10 kilogram rock or something. I'm not going to talk about it like that. So volume is a measure of liquid and gas, but we can also talk about it in terms of solids. For example, when we're figuring out the density of something, we can talk about it in terms of that as well. And when we talk about it with solids, that's when we use this one, actually, we'll say. All right, so we use centimeters cubed when we're talking about solids. Okay, so we got volume, mass, density. The last one we need to talk about is this idea of pressure. Pressure. So pressure is a force that is exerted by a substance per unit area on another substance. That's the definition. All right, and the units that we're going to see, or we're going to mostly talk about this when we're talking about gases. For example, well, let me give you the units first. So pressure is measured in atmospheres, ATM, and sometimes you might see it measured in millimeters of mercury, which is Hg, which we will explain when we get there to pressure, but when we start talking about pressure of gases. But for right now, this means millimeters of mercury. Hg is the symbol on the periodic table for mercury. Okay, so let me give you an example of pressure, how you're going to see it. So the pressure of a gas is exerting a gas has a pressure that is exerting a force on the walls of a balloon, okay? So we have a balloon here, and it's filled with gas, right? And the particles, the gas atoms or particles that are inside of this balloon, they're exerting a pressure on the sides of the balloon. And that is what makes the balloon maintain its shape here, like this, okay? So there is a pressure, there's an air pressure. Maybe you've heard of this idea of air pressure. So gases all exert a force on the container that they're held in. We're going to make a note of that. Gases exert a force, and that force is called pressure, on the container, or the walls of the container that is holding them. Container that holds the gas. So the container that's holding the gas inside of your body right now would be your lungs. So the gas that you're breathing in actually exerts pressure on the insides of your lungs, and it keeps them kind of branched, or the shape that they are. Okay? The gas that's inside the room right now, of the classroom right now, is exerting pressure on the container that holds it, which would be the walls. Okay? So you can't feel the pressure here, but if we could measure the pressure or see the pressure, we would see that the gas is exerting pressure on the walls in the classroom. Okay, so those are the 4 vocabulary words that we need to understand: volume, mass, density, and pressure, in order to now finally start talking about our different states of matter. Alrighty, so matter can exist in 4 different forms. Yes, I said 4, not 3. So matter can exist as a solid, as a liquid, as a gas, or as what's called a plasma. All right, so you'll see I put a little star down here by plasma, because we aren't going to really talk about plasma that much, because it's not one of the, it's not one of the common states of matter that we see every day, right? Plasma is it's only made in a lab, for example, or we see it in electricity. We don't see or lightning, for example. We don't see plasma in everyday situations, so we're not going to talk about plasma as much. But we are going to talk about these other 3 a lot. So first we have solids, and these are things like literally all of the things you're seeing right now. unless it's a liquid, but you can't see gases usually. So a solid is something that, a rock, a piece of sand. Your body is a solid. Most of your body, their blood and stuff is liquid, but your computer screen, your computer keyboard, the tables, the door, you get it. Solids are made up of atoms or particles that have very low kinetic energy. And just a reminder, I guess I could have mentioned this when I was talking about kinetic theory, but remember that kinetic energy is the energy associated with motion. So it's not potential energy, but we're talking about kinetic energy, actual energy associated with motion. So because of this, the particles that make up solids move very, very, very little, very, very, almost not at all. They vibrate. So this is going to make more sense. I'm actually going to talk about... No. Okay, so that is... I'm going to move this down so I can have more room to write here. All right, so the particles have very low kinetic energy, meaning that the particles move very little. They just vibrate. There are attractive forces between the particles or the atoms. And they are very high or strong in solids. So the attractive forces, meaning like all atoms have attractive forces. They can have attractive forces. Think of it as like magnets. So the particles of solids have very strong attractive forces. Those particles hold on to each other. If we were to draw the atoms of a solid, they are really close together, like this, and they really like to be right by each other, and they barely move at all. All they're doing is just vibrating. And the reason that they're not moving very much is, I'm going to draw a little, that's them barely moving. All right, and this is going to make more sense when we talk about the movements of liquids and gases, but for now, this is the motion that we're talking about. Okay, so my solids have attractive forces between them, between the atoms that make up the solid, and those attractive forces are very strong. They hold on to each other very tightly. Then we are going to talk about the shape, the volume, and the density of solids. We're going to talk about these for all of our states of matter, but obviously we're starting with solids first, so that's what we're going to talk about first. So the shape of solids is what's called definite. The volume of a solid is also definite. And the density is for solids is higher than the other two states, usually higher than other states. So, meaning that solids are the most dense. I'm going to come back to shape and volume in 3 minutes when I talk about the shape and volume of liquids. So, just bear with me. I know you probably don't understand what I mean by shape being definite and volume being definite, but it will make more sense in a second. So, I would say here than other states, and I would say for most substances, except, interestingly enough, water, for example. So ice, solid water, is actually less dense than liquid water. But for every other substance, the solid is more dense. It means it has more mass per volume. And you're going to learn about that a lot more when you get to chemistry. But water is the only substance, well, one of the only substances. I actually can't think of another one. So we'll say for the sake of this class, water is the only substance that has that whose liquid is more dense than its solid, but every other substance, the solid is more dense than the liquid, and it's more dense than the gas and plasma, obviously. Okay, so that's what you need to know for solids. Now let's look at liquids. We're going to look at all of the same things for liquids. So particles of liquid have medium kinetic energy. So they're made of particles with medium kinetic energy. This means that the particles move a little, they move past one another, they collide with one another and with the walls of the container they're held in. So they move past one another, they collide with one another, and they collide with the container that they're held in. Oh my gosh, I did not just do that. Please don't judge me. I just wrote the wrong there, but I immediately corrected it, so we're going to just pretend that didn't happen. That didn't happen. If anyone ever brings that up, you're all failing. I did not just do the wrong there. Oh my gosh. Whew. I don't know how I'm going to be able to live with myself going forward, but I'll do my best. With the walls that they are held in. All right. So this is, as opposed, to understand these things better, we have to compare them to one another to really understand. So solids have very low kinetic energy. The particles that make up solids have very low kinetic energy. Whereas the liquids, the particles that make up liquids have medium kinetic energy, meaning they have more kinetic energy associated with the particles that make up a liquid than do the particles that make up a solid. So I said that particles of a solid move very little. They actually only vibrate. But if we were to draw the same thing here, our same 12 particles of liquid, like this, you see that they're a little more spread out. If we draw the movement lines, we're going to indicate their movement is a little faster with some longer lines. I drew some just crooked lines before with indicating that the solids were just vibrating. But here, the liquids move. They move past each other. They collide with one another. They are colliding with the walls of the container they're held in, etc. So solids are just vibrating. The particles that make up solids are just vibrating, whereas the particles that make up liquids are actually moving past one another. All right, the attractive forces between atoms of a liquid are medium as well. We'll say are medium. We're just going to say literally are medium. So we have to talk about this in relation to, or as opposed to, the attractive forces of solids and of gases. So gases have very high attractive forces, but the attractive forces between the atoms of a liquid are medium. So they're not holding on to each other as tightly as do the particles that make up a solid, but they're kind of attracted to each other. They're not flying off. There's still some attraction there. They are held together. If they weren't held together, the water that's sitting in, I don't know, on the ocean would, or not on the ocean, I don't know, in a pond or in a puddle, let's say in a puddle, those particles would fly off into, fly off, right, into space if there wasn't any attractive force between particles of a liquid. There has to be some kind of attraction between those particles so that the particles don't go flying off from the surface of the liquid. So that's one way of thinking about it. Okay, so now this is going to make more sense. We're going to talk about the shape. The shape of a liquid is indefinite. The volume of a liquid is definite. And the density of a liquid is, for most substances, liquids are more dense than gas, but less dense than water. More dense than the gaseous form, but less dense. Did I say than water? I said that wrong. But less dense than water, but less dense than solid. Less dense than the solid. Okay, so that one's pretty simple. I think that's straightforward. Liquids are less dense than solids, but they are more dense than gas. But let's talk about this shape and volume problem here. So if I have a solid rock, here's my solid, beautiful solid rock, okay? This is solid carbon, all right? Okay, and down here we're going to have liquid carbon, and we're going to put this liquid carbon in a glass here, okay? And there's my liquid carbon. Okay. All right, so the shape. Let's talk about, let's talk about volume first. That's pretty easy. So remember, volume is the measure of the amount of space that a substance occupies or takes up. So let's say that the volume of this rock is 15 centimeters cubed. All right, so that's a definite volume. I could crush this rock up into a powder, right? I could crush this solid carbon. It's not a rock, I guess it's charcoal. Anyway, I crush, or coal. If I crush this solid carbon up into a powder, it's still a solid. Powder is a solid, but it will be still 15 centimeters cubed, right? If I put it into, I don't know, if I chiseled some off, or if I broke it into 10 pieces, or no matter what I do, it's going to be 10 or 15 centimeters cubed, right? So that's a definite volume. Solids have a definite volume, okay? Liquids have a definite volume too. If this is, let's say this is 15 milliliters of carbon, whether I put that 15 milliliters in a little or a really big container, and it's just at the bottom, it's still going to be 15 milliliters. If I put that carbon in a really super tall glass, like this, it's still going to be 15 milliliters, right? So the 15 milliliters is definite. We're not going to change the volume of this liquid. However, what you're seeing here, what I just drew, is this liquid in the form of 3 different shapes, right? In this container, it has a kind of medium height, medium width. It would be, if you imagine this is a real life rather than a 2D drawing, this would be a cylinder, right? The shape of that carbon would be something like this, right? And the shape of this one down here would be something like this, right? And the shape of the really tall, skinny one would be something like this, right? So the shape is not definite. The shape of a liquid depends on the container that the liquid is in. You should write that down. The shape of the liquid depends on the shape of the container that the liquid is in. All right? So as opposed to this rock, for example, this shape, I could put this rock, or this solid carbon. If I put this solid carbon in a glass, just the way that it is, if I don't, if I just set it in a glass, or I set it on a plate, or I set it on the table, it's not changing its shape based on anything, right? If I did physical things to it, I could change its shape, but it doesn't take the shape of its surroundings the way that liquid does, right? It stays that shape until I force it to make it different, change its shape, right? So that is what I mean by definite shape and definite volume for solids. And this is what I mean by indefinite shape for liquids and definite volume for liquids. All right. Let's see how much time we have left here. All right, so I'm going to go over all of these things pertaining to gases, and then we're going to be done for the day. So our third state of matter is the gas, or the gaseous form. So I've given you examples of gases. Gases are the air you breathe, helium that goes into balloons to make them float, oxygen, hydrogen gas, nitrogen gas, water gas, steam. Any substance can turn into a gas. Any substance can go from a liquid actually to a gas, if we give it enough energy. So the particles of gases, have a lot of kinetic energy. They have high kinetic energy. So if something has high kinetic energy, obviously that means that the particles are going to move a lot faster, right? Than they do, for example, for like liquids or gases. So these particles run into the container, they run into each other. Particles run or collide, we'll say not run into, collide with each other and with the container that's holding them. And when they do this, when they run into each other and when they run into the container that's holding them, this creates pressure, creating pressure. So pressure is just the collision of molecules, gaseous molecules, running into the sides of the walls and running into one another. Okay, so the attractive forces between the atoms of a gas are very low. In fact, there is none at all, no attractive forces between the particles of a gas. So this means that when the particles run into each other, they actually bounce off of one another. Oh, I forgot to draw my little gas particles here. So the gas particles are super spread out, and they're moving super fast. So I'm going to draw super long lines. Wow, they're going so fast. All right, so I think you get the picture. And when they run into one another, their collisions are what's called elastic. They bounce right off of one another. They don't, like when a liquid particle runs into another one, they kind of stick together and slowly move past one another, right? But with particles of gas, when they hit each other, they bounce right off of one another. There's no attractive force whatsoever between them. So we'll say, not in red, elastic collisions. Elastic collisions between particles. I've run out of room, and this is annoying. All right, there we go. I just had to make it a little smaller. Okay, so the shape, the volume, and the density. So I just told you that gases have, that the particles are super far apart from one another. So they have way less density than liquid. They're way less dense. Less. That looks like less spelled with 3 S's, which is, we all know, incorrect. Way less dense than liquids. So these are the, well, until we talk about plasma, but we're not going to talk much about plasma. So then gases are the least dense of the 3 main states of matter. The shape of gases and the volume of gases are both indefinite. Indefinite. So what that means is that when I put a gas in a container, just like a liquid, it takes the shape of that container. So I'm going to draw 3 different containers here. All right, so here are my 3 different containers. I have, let's say, a 1 liter container, a 5 liter container, and a 15 liter container. Okay? Or we could have done this, I guess, in centimeters cubed, but whatever. Okay, so I'm going to have the same amount of gas each time. I'm going to have 5 particles of gas, all right? Or let's do 10. When I put those 10 particles of gas, there's a trait that gas has. Gas fills up whatever container it's in. It will completely fill it up. They will all be evenly spaced. Those gas particles will be evenly spaced throughout the container. So what I mean by that is, if I put my 10 gas particles, I'm going to take these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gas particles, and I'm going to put them all in my first box. All right, so those 10 gas particles are going to take on the shape of this 1 liter box, and they're also going to have a volume of 1 liter, right? They spread out evenly. But if I take those 5 gas particles and I put them in my 5 liter box or container, now they have taken on the shape of the bigger box, and they've taken on the volume of the bigger box. Now they have a volume of 5 liters. And of course, if I take those 5 or 10 gas particles, I think I said 5 last time, sorry, and put them into my 15 liter container, now those 10 gas particles have taken on the shape of the 15 liter box. So they're a bigger shape than they were before. And they are now 15 liters. The gas is 15. I have 15 liters of gas here, rather than having 5 liters of gas here in the middle, or 1 liter of gas here on this side. So as we increase the size of the container that the gas is in, we decrease the pressure. We're going to see that here in a little bit. But remember that the pressure is just these particles bumping into the sides of their container and bumping into one another. So if there's more volume here, we're going to have less pressure, right? Because those particles are going to have a lot more space to move around. It's less likely that they're going to bounce into the side of the container or into bounce off of one another, right? Anyway, so indefinite shape, indefinite volume. Gases take on the shape and the volume of whatever container they're put into. That's something you should write down. Liquids, remember, only take on the shape of the container. I told you to write that down, but we'll write it down here again so you remember that you definitely have it, or make sure you definitely have that written down. All right. And then, of course, solids don't take on either the shape or the volume of a container that's holding it. All right. So those are all of the different kind of characteristics of liquids, solid liquids, and gases that we're going to talk about. Let me check how much time we have left. Okay, no time left at all. All right, so we are halfway through section 14.1. I am not going to give you homework. We will do an assignment on Monday. So that is it for today. We will finish 14.1 on Monday, and you'll do some questions then over all the stuff that we've gone over today and whatever we go over on Monday. So that is it. Have a good weekend, and I will not see you, but I will see you on Monday. Have a good weekend. Bye.